Now everybody loves a campfire. You can sing around the campfire, you can laugh and tell stories with your friends, you can maybe have a s'more or two, or share in a marshmallow if you don't like chocolate, or graham crackers. But let's say you were trying to come up with a way of establishing the enthalpy change of a reaction, like a combustion reaction such as the case in a campfire. Well, you probably won't be able to do this underwater in a coffee cup calorimeter with any effectiveness. So there has to be some way in which we can establish the overall enthalpy change of a reaction that's not easily performed in a coffee cup calorimeter. So how do we go about doing this? Well, we use something called Hess's law, which really just concerns itself with the relative difference of the energy between the reactants and the products, and really doesn't concern itself with how it got from A to B. That is, there are different reactions that will result in products from a certain type of reactants. That is, these reactions can take different pathways depending on the conditions under which the reaction takes place. So Hess's law really just looks at the start at the beginning. It doesn't look at the path and how it got there, and we refer to this sometimes in chemistry as a state function. Now let's take an example of what this might look like. Again, we're dealing with just the relative change between the reactants and the products and the enthalpy change between the two. So if we take, for example, the combustion of methane. So we have CH4 under the combustion of methane in the presence of oxygen. If we just take a look at the direct path, we can see that there is an enthalpy change of 890 kilojoules. But this isn't the only way that methane can combust to form carbon dioxide and water. There are other ways to do it. But what you may notice is even though there is a different pathway for the combustion of methane, it still results in the same products. And if we add up those enthalpy changes, they are still the same absolute value between the reactants and the products. And this is true for all thermochemical reactions. So how can we use this? Well, if we think about a target equation, that is the reaction that we're looking for, we can take individual reactions and add them up to equal the total enthalpy change of the system that we are looking at. So in a typical Hess's law problem, you're going to be given a target equation. And then you're going to be given some other equations that you can use or manipulate to arrive at that target equation. So we can see here that we have a target equation for the production of butane, involving carbon and hydrogen as our reactants. Well, we don't have the enthalpy change for this particular reaction, but what we do have are a series of other reactions that we can use. And so the way that this works is we try and manipulate these given reactions in order to add up to the overall reaction or the target reaction that we're trying to find. Algebraically, we're going to rearrange these equations to arrive at our target equation. So let's take a look at the first one and notice that butane is on the reactant side of our given equation. And on the target side, it's on the product side. So we're going to do a reaction flip. We are going to flip this first reaction so that our butane now is on the correct side for our target equation. That is, it's on the product side. Notice what happened to the change in enthalpy. It went from a negative value, or an exothermic value, to an endothermic one. Anytime you invert the equation or multiply it by a factor of -1, you have to do the same thing to the enthalpy change for that reaction. So now we're in a good place. We have this butane on the correct side. If we take a look at our second equation, we have carbon on the left side, we want carbon on the left side. But notice that we have 4 carbon in that target equation. So we're going to have to magnify the amount of carbon that we have. We're going to have to scale it up. So we're going to multiply it by a factor of 4. And anything you do to one thing in a particular thermochemical equation, you have to do to everything else, including, as you'll notice, the enthalpy change. So we have to multiply that and everything else in it by a factor of 4, and then we're going to have the 4 carbons that we're looking for. And if we look down at that last equation, we can see that we want to have 5 hydrogens on that reactant side. We already have 2, so we're going to have to multiply it by a fraction. Now, fractions are okay in balancing chemical equations for thermochemistry, because we're only looking at really the change per mole. So, because we're dealing with moles, fractions are okay because we have such a large quantity of particles. So we're going to multiply this by 2.5, or 5/2. And in doing so, we multiply everything again in that equation by 5/2, or 2.5. And that's going to lead us to the 5 hydrogen that we're looking for. But ultimately, if we were to add up or take the sum of all of these individual equations right now, they wouldn't equal our target equation. We have to eliminate some of these things that we notice appear on both sides. Notice that we have carbon dioxide appearing on both sides, so we can cross it out or eliminate that. And various other things that we have in here, we can eliminate as well if they appear in the same amount on both sides. Now notice what we're left with. We're left with those substances, our carbon, our hydrogen, and our butane on the appropriate sides. So now it's just a matter of adding all of our enthalpies up, and we're going to arrive at the total enthalpy change for this particular reaction. And this is an effective use of Hess's law. So let's take a look at some tips for using Hess's law. Always arrange the equations so that all substances are on the correct side of the arrow. And we did that for that first equation in our previous example. Scale the reaction so that the number of each substance is the same as the target equation. So if we're looking for 4 carbons, we had to scale or multiply that entire equation by 4. We're going to cancel out all unnecessary substances that are represented on both sides of the arrow once we add up our equations. And then whatever's done to any equations, and this is the most important part, must be done to the enthalpy value for that equation. Anything that you scale or invert must be done and to the same magnitude to the enthalpy change as anything else in that equation. And if you keep to these tips, you'll have no problem applying Hess's law to any sort of scenario. So if you're looking to watch this video again, or if you're looking for some additional videos on some of the chemistry topics you've been covering in class, take a look at our YouTube channel or follow us on Twitter. Thanks for watching.